I'm hearing about all these different techniques. There's also this term called a model tournament. That's when you take multiple techniques like the neural network or the gradient boost or the linear regression or decision trees, and you kind of stack them up against each other and you say, which one's the best?
That's exactly right. Doing a model tournament is the ultimate way to figure out what is that best model. Hi everyone, it's Brian Amrine here with Value Driven Analytics, and I'm here today with a very special guest. You've seen him before, Gary Spakes with Rich Trail Ventures. Happy to have you on the channel, Gary.
Yeah, it's been a fun conversation that we've been having over the last couple of times here. You know, we started out looking at the whole analytics lifecycle and that analytics process with preparing data and then exploring data and then building analytic models. That's where we're going to be spending the time today. But that's even not the end of this process, because you got to validate those models and put them into production and then visualize all of that as well. So we have a lot of ground to continue to cover here.
Yeah, no shortage of work when it comes to analytics and data science.
Yeah. So just as a recap, we talked data preparation, and that's really shaping your data for a problem, and then data exploration, where you're looking at target variables and independent variables and what that means, and how you could actually have to iterate back to data preparation because you don't have the right data. It's associated with what your problem is, or your association analyses or analyses. Oh, there you go. Yeah. They're not getting to the point where it's identifying all the right independent variables and things like that. I think we have some use cases around not only sales, but like car OBD readers, the manufacturing side.
Kind of interesting.
Yeah. And now, when we think about building an analytic model, we're moving from that descriptive analytics side or statistics into things like data mining and text mining and forecasting there. And I'm going to talk a little bit about that one category of this predictive analytics space, that's data mining. So, what are some of the problems that data mining can actually help solve?
Yeah, I think you've got predictive and prescriptive use cases. Most analysis comes down to that. So when I think about some of the things I've done in the past when it comes to data mining, trying to find an insight, something unusual, something unexpected with data, I think about maybe using a tool like Python, or you could use SQL to automatically flag outliers or things that have changed the most. Now, some things are expected to change based on their previous seasonality. You always know that sales for ice cream is going to go up in the summertime. It happens every year. So if starting around April and May, you see a spike in ice cream sales, that doesn't mean your data mining should flag that and say, guess what, management, we're getting a big spike in sales. This is amazing. They're going to say, that happens every year. Tell me something I don't know. But if you see that controlling for seasonality, maybe looking at year-over-year growth and looking at that over time that does control for seasonality, and you start seeing a particular segment of products going up in that metric, now you've got something to flag. And rather than going into Excel or even a Power BI, even a dashboard, and looking at for these manually, well, how does this product look for the latest week? How about this product? Why not creating a script in Python or SQL that automatically runs and flags which segments are seeing the biggest unexpected change, the change after controlling for seasonality, maybe even trends, like maybe a segment has seen a lot of growth, but you've been seeing it for the last few months. It's nothing new. If you were to go to management and say, guess what? This product is growing a lot year over year, they'd say, yeah, it's been growing at that rate for the last 3 months. We've been talking about that in the last 3 monthly business reviews. It's great to hear that it's still growing, but unless that growth dramatically changes, or starts going down or going up, it's not necessarily something we should be focusing on. We want to hear about what's changed the most since the last time we spoke. And so when I think about data mining, I think about setting up automated process around that. So it's not a analyst having to look manually filtering on different cuts. It's you run a script that you've created, maybe it's automated, and maybe it's automatically emailing you when there's something unique in the data.
Yeah, I think what you're talking about is a little bit further down the path from where I was thinking to begin with. I think you're talking about putting a model into production and having the results come to you on that. But if I roll back to data mining in and of itself, I think about things like market basket analysis or things like recommendation engines, those types of things. Like market basket analysis, because you bought this, you might like to buy that. People who bought this also bought this. Or a recommendation engine, because you watch this show, you might like to watch this show on stuff like that.
That's right.
But there are different analytic techniques in that analytic build. Once you've got the terms that we were talking about the last time were like target variables and independent variables and things like that. But there's different analytic techniques that you use in data mining.
That's right.
For some of those, like what are some of those, and why would you use one versus the other?
Oh boy, there are all those things you mentioned I would consider to be data science models. There's so many ways of classifying data science models. And a lot of times it comes down to your use case. What's the business challenge? So there are, for instance, one very popular categorization of models is supervised models versus non-supervised models. And non-supervised models would be models that don't have a target variable. Oftentimes, not always, but oftentimes use non-supervised models to group similar observations together. It's a clustering, for instance. There's all kinds of clustering methods that use this. Principal component analysis is another type of non-supervised model, but it's all about grouping things together. So if you have a challenge where you want to put people in groups based on similar categories, that would be something to consider, a non-supervised model like k-means clustering or another form of clustering.
Yeah, I think I like decision trees for that, like male, female, 25 to 34 male, 45 to 54 male, things like that. I think about decision trees and doing some of that as opposed to actually using a decision tree model to get to a specific answer.
If you have a use case where there's a target variable involved, then you're looking at supervised models like a decision tree.
Okay.
So for instance, let's say to start with, you think, well, I just want to create similar groups and I want to do something with that. I'm going to manually perhaps take each group and talk to them and figure out what resonates with them, and that'll design different treatments for each of those clusters that get created. Maybe that's your starting point. But perhaps it turns into a supervised model eventually where you have these characteristics. If you just train it on a non-supervised model, a clustering model, you might put people in similar age groups and genders together. And so that'll give you some clusters. But if your end goal is, well, I just want to figure out which one based on those categories, which product that we offer, they're most likely to purchase. Now you're getting to maybe a supervised model where you can go in the past and you've got this list of customers with their age and gender and so forth. And your target variable is which product did they purchase? And you're creating a model. We talked about this a little bit last time, a separate model for each product. Did you buy this or not? A binary target variable. You put them through all of your products. Each person you score on each one of your products that you offered, and you try to sell them the product that they have the highest likelihood of buying based on the characteristics you know about. So now you've turned to, maybe it was just initially putting people in similar categories, not looking at what they bought at all. And now you're turning into a supervised model where there is a right answer. So you're using something like a decision tree or regression or other type of machine learning model to actually use past data to predict what they're going to buy. That's a supervised model because we have a right answer.
So you just said you have a right answer. How do you get that? I mean, there are terms that I've heard in the analytics space around logistic regression, linear regression, gradient boost, ensemble models. You mentioned principal components earlier, neural networks. I mean, there's all these different analytic techniques that are out there.
Absolutely.
How do you know which one's the right one to use?
Yeah. Well, principal component analysis, that's one of that's the only one you mentioned that's non-supervised. So that would be in the no-supervised category. If you're just trying to do a grouping analysis and don't have a right answer, that's probably where you want to go. It's the non-supervised techniques. But for all the other ones you mentioned, those are supervised techniques. So in the example where we do we have a historical data set and know which product they ended up purchasing, that's a great use case for a supervised model. But to your point, there's a lot of supervised models out there. There's parametric models that assume a distribution like regression, and then there's non-parametric models like machine learning, which, gradient boosting, random forests, decision trees, neural networks. There's all kinds of non-parametric machine learning models out there too. And they all, at the end of the day, do something similar. There's a target variable and input variables, and you're either trying to predict something or explain something. And so in order to figure out what the right technique is, there's a few considerations. One is your use case more predictive in nature, or are you really trying to or even if it is predictive, I really need to understand what the model is doing. Maybe because you're doing something that's regulated, like the medical or financial industry, where if I'm declining someone on a loan application, I need to tell them exactly why. Then perhaps you consider more of the more explainable models in that set of supervised models, like regression is one of the most explainable models you can have. So a lot of credit scoring models are based on regression. But if it's more of...
But that may not be the best technique.
It may not be the most predictive technique. Exactly. You might be able to get more benefit.
But it is the most explainable.
It's the most explainable.
Okay.
But if the explainability is kind of secondary, that'd be nice to have. I really just want to get the most accurate answer. Then you're looking at probably more machine learning models that often, not always, but often do the best job. And it's a question of bias-variance tradeoff when you think about which model is going to be the most predictive.
Yeah. Well, at the end of the day, it's just math, right?
It's just math, but some models are more complex and in some cases perform better from an accuracy perspective than others. They're at a different point on the bias-variance tradeoff continuum, and that determines which model is going to be best for which situation.
Oh, so kind of like the difference between multiplication and geometry and differential equation.
Right. It's a continuum of complexity, yes. And so when you think about the more complex models, they tend to really there's two ways of reducing error or increasing accuracy. One is to reduce the bias, which essentially means find the most relevant set of observations for the one in question that we're predicting, and just mainly focus on those observations. Now that's good from a relevancy perspective, but since you're reducing your pool that you're making assumptions on, it increases your variance. Now the two things that help your accuracy is reducing that bias, making decisions based on more relevant observations, but also reducing the variance, which a lot of times involves using a larger population of data points. When you make a prediction, that generally reduces the variance. But what happens in modeling, all kinds of modeling decisions are impacted by this bias-variance trade-off. And so some models really try to make decisions on specific data points at the expense of higher variance. And those are your models that sometimes, especially if you have large data sets, have more accuracy, but they're also less explainable, and they sometimes won't do as well on data sets that are maybe just 100 or 1,000 observations.
Got it. So, when I'm hearing about all these different techniques, there's also this term called a model tournament. And that's when you take multiple techniques like the neural network or the gradient boost or the linear regression or the decision trees, and you kind of stack them up against each other and you say, which one's the best?
Yeah.
Right?
That's exactly right. Doing a model tournament is the ultimate way to figure out what is that best model. Is it the neural network or is it regression? Again, in general, there are some, if you have a smaller data set, regression might generally perform better than a one that focuses on reducing the bias the most, like neural network. But the best way to figure that out is to try a range of models and then you score them, and this is key, on a holdout data set. You see, neural networks...
Right. Okay, so explain to me a holdout data set. What's that mean?
Before you even start to model, when you create your data set, you've written SQL or Python to create your data set, what one row represents and everything.
Which we talked about in the data preparation exploration phases in previous videos.
So check that out if you want more information on that. But once you create that data set, there's a few techniques you can use to create a holdout data set. A very common one is to take 20% of your data, of your data set you've created, hold it out. You put in a separate data set. You're not training your model on that. It'll be used for validation. So sometimes you hear the term validation or test or holdout data set, all same thing. It's just different words for the same thing. You put that aside, you train your model on the 80% of your data set that's remaining, and all this is randomly selected, the 80% that you train on versus the 20% that you validate on. You build that model on the 80%, and then once you built that model, you apply it to your testing data set, and you assess the performance on that testing data set. That's important because some models are prone to overfitting more than others on your training data set. A neural network, for instance, a random forest will overtrain on your data set. It'll look great on your training data set.
And that's what you mean by overfitting. It looks great because it just
keeps training. Imagine like having a variable that's something like, my name, when your name is Brian, you buy, if they've seen that I've bought in the past, training a model on that, but then applying it to something else and not seeing any accuracy when it sees other people with different names. That's maybe just a high level example of overtraining, but it gets too specific to the data. It has really fitted the model parameters to that training data set too much, to the point where when you apply it to that validation data set, that data set it's never seen before, the accuracy just goes to pieces.
Okay.
It's completely different.
So these modeling techniques that we've been discussing, and you have your training data and your holdout data.
Yeah.
Does the model techniques work on every row in that data, or is there sometimes where the data is just thrown out?
Well,
or the row is thrown out?
Yeah, that's a good question. You want to craft your data set in such a manner where it is
useful.
Yeah, and it's making a decision, or has the potential to make a decision on every row. If you're using regression, for instance, it will use every row in the data set.
Regardless of what the values are.
Regardless of what the values are, as long as, and this is key, that you don't have missing values.
Missing.
Yeah.
So is it any column, or is it columns from your independent variables that if it's missing, it gets chunked?
Well, you've got independent variables, you've got a target variable, and it depends on the advanced analytics tool you're using on how it'll handle that. Python, R, SAS, even the libraries used within those will handle it differently. A lot of the libraries will simply throw an error. If you have a missing value in your independent variables or your target variables, it'll just throw an error and it won't even run the model. It'll tell you that there's missing values and those need to be addressed. Either, especially a lot of data scientists who are just starting out, they might say, I guess I'll just drop the rows that have missing values. I would recommend against that in most use cases. You still want to be able to score those. You might be able to come up with a good prediction for them based on the other input variables that aren't missing for those.
Right. So you have to either fill in the missing value or remove that independent variable from your calculation, right?
You could do that. I would rarely recommend removing it from your calculation. I would at least assess the value. Perhaps it only comes into play, perhaps it's only populated 5% of the time. But for that 5% of the time,
it rocks.
It rocks. And in some cases, even the fact that variable was missing can provide some predictive information and help you make a better prediction. Just the fact of whether it was missing or not.
So if you want to use those rows, you've got to impute that variable if it's missing. And imputation is an interesting thing as well. I think about, do I just put, like, if it's a number, do I put a 0 in it? Or do I put the minimum value that's the ones that are there, or the average or the maximum value? Am I on the right track here so I can actually get use of that row and the other variables?
You're on the right track. Exactly. And it comes down to the business in the space.
So we're talking about imputing variables with a 0 or a minimum or an average or maximum, or, is there other types of being able to calculate these variables?
Absolutely. It comes down to the business use case. It
always comes down to the business.
It does. The whole design of the model comes down to the business use case, but also how you impute values would come down to the business scenario. So in some cases, a value is missing. I'm thinking about, for instance, starting with a list of customers, and maybe some of your input variables are how many sales that they had the last 30 days, last 60 days, last 90 days. And so going back to our SQL videos, you left join in a data set of sales, and in some cases it'll be missing. In that case, having a missing value for sales means that they didn't have any. So replacing those values, those input variables with a 0 would be the best technique in that case. Now, in other cases, if you have, maybe you have something where you're bringing in zip code demographics, but your zip code data set has a few zip codes that are missing. And so when you join that in, some of your things like population density for that person's zip code is missing. That doesn't mean the population density is 0. You wouldn't want it 0 in that case. It's missing. So there's a lot of ways to handle that. One of the simplest ways that I'd recommend is first, before you try to replace the value, create an indicator for whether it was missing in the first place. Again, sometimes just the fact that that data was missing ends up being predictive.
Okay, so when we talked about data preparation and data exploration, we talked about potentially iterating from the exploration phase back to preparation again. Now you're telling me that when we're doing the modeling and building the analytic models, they may have to iterate back to preparation again?
Yeah, a little bit. And now, that doesn't mean you're going to necessarily update the whole database structure of tables, unless if that was a very popular variable you were going to create for a lot of different models, maybe it does make sense to add some missing indicator variables to the core data set if they're being created a lot of times. But in this case, most likely you're an advanced analytics tool, you're in Python, R, SAS, and absolutely you're adding to your data set. So the best thing you can do is anticipate that. Before you even get to the modeling process, don't even try to run your model until you validated that you don't have any missing values. And so that's one of the things you do in the data prep stage is you look for missing values, you create missing indicator variables because that indicator variable can be sometimes predictive in itself what it was missing. And then you impute in your original version of the variable, population density, for instance, maybe you impute the median wherever it's missing.
Okay. And we can also do imputations on segments of your data from a distribution as well. So you can really get into some fine tuning of how you impute variables for these analytic techniques that would throw out these missing values too.
That's right. You can get really fancy when it comes to the imputation techniques. And this is where I would recommend a minimum viable product approach, where maybe for starters, you just impute the median. But if the model ends up being really successful, used a lot, you want to optimize it from there, try to get the remaining 20% of value that you could get by making it even more predictive. That's where perhaps you start building models to predict that value.
And this is where we were talking about last time that perfect is the antithesis of good, and getting value early and then refining that value as you go along. Oh, yeah, this has got some really insightful information that is providing. Let's see if we can actually make it better, as opposed to trying to make it as best as it could be right off the gate. Is that right out of the gate?
That applies to how you impute values. Start simple, maybe come back to do something more advanced. It even comes into play with the models that you try. Perhaps to start with, you choose a model that you think is going to work really well, or maybe a set of models. But then down the road, you come back to even that decision and try even more data science models to see if there's certain algorithms that give you more benefit. But don't try to boil the ocean at first. Just try to get that minimum viable product as quick as possible. Something you think would add maybe 80% of the value. Get that in the market, see how it does, and then come back to it if it's actually being used and driving value, and optimize it from there. That's my recommendation.
Yeah, so we've talked a lot about data modeling and some of the data side of mining, the data mining side of all of this. And I know in the predictive analytics space, there's forecasting and text mining as well. In the next time, let's talk some more about forecasting and what does that really mean, and what's your data got to look like for that. We've also talked about iterating back to data prep and data exploration to get to the point where we're modeling that data as well. I want to thank everyone for joining us today. My name is Gary Spakes for Ridge Trail Ventures, here with my friend as a guest, Brian Amaron from Value Driven Analytics. And let me tell you, If you've just been watching Brian with the data preparation components and the SQL side of the house, you're just scratching the surface of what what value he can bring to you, what expertise he can bring to you. So please join us in the next one as well, Brian.
Yeah, thank you, Gary. It's been a pleasure as usual, and would recommend that any of our viewers who have data challenges also consider Ridge Trail Ventures. Looking forward to partnering with you, Gary, and I really appreciate you joining us today on the channel. If this has been enjoyable and helpful for you, please consider liking the video. If you'd like to see more interviews, me and Gary, but also just some general analytics training videos, please consider subscribing. We'd love to see you back on the channel.
Drop us a comment.
Drop us a comment, absolutely. If you have questions about what we've talked about today, drop us a comment, and we hope to see you on the next interview or training video.